Good afternoon, everyone. And in case you are remote, also good morning, good evening, and good night. I'm Zhao from University of Illinois, and I'm going to present our work, Binoculars, Contention-Based Side Channel Attacks Exploiting the Page Walker. Modern processors have many side channels, and they all have the same root cause, which is the shared hardware resource between the victim and the attacker. Depending on the types of the resource, we can classify channels by two orthogonal dimensions. The first dimension is whether it's a stateful or stateless channel. A stateful channel encodes information through a persistent state change, like cache-based attacks, while a stateless channel encodes information through temporary resource contention, like port contention attacks. Because contention effects are usually small in stateless channels, they are considered harder to exploit than stateful ones. The second dimension is whether the information in the channel is a direct result of victim micro-ops. Examples of stateful indirect channels are those leave TLB or cache footprint because of address translation or hardware prefetcher. Usually, indirect channels are easily overlooked by side channel defenses. Now, the question is, do we have any stateless indirect channel? In this work, we present the Binoculars Attack, the first stateless indirect channel. The Binoculars Attack is a cross-hyperthread side channel on Intel processors. It exploits the resource contention between page walk operations from one thread and normal memory accesses from the sibling thread. And I want to emphasize that this is temporary resource contention and is not due to the cache footprint. We found that the binoculars have many novel behaviors. For example, unlike prior stateless channels, the binoculars attack is very easy to observe because it can create a contention up to 20,000 cycles with a single dynamic instruction. Also, it leaks a wide range of virtual address bits. To understand the binoculars attack, we have to first understand the virtual address translation and page walk. When a core tries to access a virtual address, such as load from VL1, we have to translate VL1 to a physical address first. To do so, the core looks up the TLB, and if the lookup results in a TLB miss, a hardware structure named the page walker will initiate a page walk, which essentially is to read the virtual to physical mapping from the page table in the memory. On x64, to perform a page walk, the virtual address is divided into an offset and a virtual page number. The virtual page number is further split into 4 PL indexes, and each index is 9-bit long. During the page walk, the page walker uses the PL4 index to index into an array of page table entries, and each entry is 8 byte long. This step is accomplished by issuing a page walker load, and on Intel processors, this load goes through the L1 cache to speed up the translation. Also, its address is partially determined by its corresponding PL index. Then, the hardware page walker will just repeat this process in a fashion of pointer chase until the translation completes. Although the page walk seems quite complex, there are actually only 3 key takeaways we need to remember to understand the binoculars attack. First, page walker issues multiple, in this case 4, page walker loads. Second, address bits 11 to 3 of a page walker load is determined by its corresponding PL index. And finally, page walker loads go through the cache hierarchy and are subject to resource contention. Now, here is a surprising behavior that we observed on Intel processors, which leads to the binoculars attack. We found that if the hyperthread 1, the reader thread, is performing a single TLB missing access, which triggers a page walk that reads from RA4, RA3, RA2, and RA1, while the sibling hyperthread 2, the writer, keeps writing to an address WA, a strong resource contention can occur if the WA is 4K aliasing with any of the RAs. And by 4K aliasing, it means that they are sharing bits 11 to 0. As a result of this contention, the page walk operations from the reader thread can be delayed for up to 20,000 cycles all stemming from this single page walk. And this delay occurs regardless of what level in the cache hierarchy the page walk loads read from. This surprising behavior has two security implications. First, we can build a channel with a high signal-to-noise ratio because this delay is so obvious. Second, the contention is address-dependent. Therefore, we can use it to monitor victim memory access patterns. To exploit this behavior, we built two attack primitives depending on whether the attacker is on the reader or the writer thread. The first primitive is called the start-to-load channel. In the channel, the attacker is the reader that triggers page worker loads while the victim writes. If the page worker loads are fork aliasing with victim writes, the attacker can observe a strong contention, therefore learn the victim starts offset. Because page worker loads are aligned to 8-byte boundaries, we can monitor offsets with an 8-byte subcache line granularity. Here's a demo of the start-to-load channel. In the demo, the writer keeps writing to a secret offset 0x528, and the attacker on the reader thread will allocate 512 continuous pages, which can cover all possible values of the PR1 index. Then, for each page, the attacker flushes its translation from TLB, times an access to the page, and triggers a page walk. If the attacker is accessing a page whose RA1 offset equals to the star offset, then we are going to observe a latency increase. Here's the attacker measured latency, and we can clearly see that there's a huge spike at the secret offset. The second primitive is called the load-to-start channel, which switches the role of the writer and the reader, and in this case, the attacker writes while the victim performs a page walk. And if the write is fork aliasing with any of the page worker load, then the attacker can observe a victim slowdown, therefore learn the set of PR indexes of the page that the victim accesses. With some more information, we can even reconstruct the entire victim virtual page number. More details and demos can be found in our paper. Now it's time to discuss the root cause of this puzzling behavior. To answer that, we relied on performance counters, sometimes even undocumented ones, and Intel's patents. We found that the contention is a result of an optimization that issues page worker loads as stuffed loads, which bypass the instruction scheduler to avoid any scheduling latency. We believe this optimization has an unexpected effect, which is that the scheduler cannot detect and mediate the conflicts between stuffed loads and normal stars. As a result, the writer is allowed to run at a full speed without realizing the reader is starving. Eventually, the starvation will trigger a watchdog alarm to abort and restart the page walk with a higher priority only after 20,000 cycles. Please check out our paper for more details on the reverse engineering part. Next, I'm going to discuss an end-to-end binoculars attack on real hardware targeting Montgomery ladder and ECDSA. ECDSA is a widely used digital signature algorithm, and one step during signing is to compute the point k times g, where k is the nonce and g is the base point. One interesting fact about ECDSA is that if we know the nonce k and its corresponding signature, we can derive the private key used for signing. Therefore, our goal is to learn the nonce k. But this is a challenging task because the nonce k changes at every victim run and it never repeats. Therefore, it requires a channel with a high signal-to-noise ratio, like the Binoculars Attack, to extract the k with a single victim execution. And our target here is an implementation that uses a Montgomery ladder to speed up the signing process. Here's a simplified code that we are targeting. The code iterates through every bit of the nonce k. Each iteration, it checks the ith bit of the k, and depending on its value, it calls functions madd and mdouble with different arguments. We don't have to worry about what each function does in detail, but only need to know that if ki is 1, it writes results to big numbers x1 and z1, and mdouble writes to x2 and z2. But if ki is 0, the order is reversed. Although this code is data oblivious to the sequence of operations and end-to-end timing, it has secret-dependent reordering of stores. And if we can detect which order occurs with the store-to-load channel, we can recover the nonce k. To do that, we will pick one big number, such as x2, and monitor stores to such a variable. When those stores are happening, we will see a latency increase. And if the latency increase is in the second half of an iteration, we know ki is 1, otherwise ki is 0. Note that, unlike prior examples, the functions we are targeting here do not have enough store instructions to build the contention to its maximum value, 20,000 cycles, but nevertheless, the contention is still very obvious. Here is a snippet of the attacker measured latency. We instrument the executable to collect the timing information of iteration boundaries, mark the halves of iterations, and the value of ki. From the plot, it's clear that if ki is 1, we see significant latency increases in the second half of an iteration, and if ki is 0, those increases occur in the first half of iteration. And note that, in practice, we do not rely on these oracle boundaries, but instead, we use signal processing on row traces to recover these boundaries and predict the value of ki. And we can also handle samples that are not very obvious, like the second one here. Overall, our evaluation achieves a high accuracy with reasonable remaining brute force attempts. Besides attacking ECDSA, in the paper, we also demonstrated an attack on Linux kernel ASLR with our load-to-store channel. With our load-to-store channel, and that can bypass software mitigations and achieves 100% accuracy. To summarize, the Binoculars Attack is the first stateless-indirect channel. It exploits the contention between page workloads and normal memory accesses. And there are 3 important things we need to remember about the Binoculars Attack. First, it's very easy to observe because it creates a contention up to 20,000 cycles. And that results in a channel with a high signal-to-noise ratio, and we can extract the nonce k with a single victim execution. The second thing is that we built 2 attack primitives, and they can leak a wide range of virtual address bits. And the final thing is that please remember to check out our code on GitHub, and that concludes my talk. Thank you.